My question was precisely related to the last slide that you were showing. So this coefficient C6 that you had, it wasn't clear to me if it is something finite or something that you need to renormalize.
No, this is
because the other C coefficients that you had previously, C1, C2, C3, were divergent.
Okay, so you absorb the divergences in these coefficients, which they're finite, but you don't know their value until you measure them. So
you
that's
renormalize.
Sorry.
So you have to renormalize that quantity.
Exactly. Yeah.
It's not something that you can compute, in other words.
Precisely. Unless you match it to some UV complete theory, and actually for these terms you can do that. There are nice papers by Dieter Lust and his group where they calculated the coefficient of these operators for different compactifications. So that's a game you can play.
Okay.
But that's the limitation of the EFTs, that you simply do not know the value of or you cannot calculate the Wilson coefficient, the local Wilson coefficient.
Sure.
So next question, John Donoghue, you can unmute yourself and ask.
So did I get called on there? I didn't hear myself. All right.
Sorry?
Anyway, let me make the comment then. This is actually a comment that I was hoping Andrei Barvinsky would make, but since he didn't raise his hand, I'll make it on his behalf. And that's I mean, there are many comments I could make. This is one I think is important to say, is that really third order curvature is not the R cubed term that you've written down, the local R cubed term. There is in the effective action an expansion that's third order in the curvature that goes like R squared 1 over box R, that Barvinsky and Vilkovisky have categorized, and their collaborators have categorized in great depth. And that's at the same order in the derivative expansion as is the R log box R, because they're both order 2 derivatives. And it's certainly way dominant over the local R cubed piece. So
to have a 1 over box, you need some mass scale in the numerator. So if you integrate massive objects, yes, you will have those.
No, that's the mass. That's the Barvinsky-Vilkovisky curvature expansion of the quantum effects.
So
you have the local terms at R squared. You have R log box R type terms.
That's right.
R squared 1 over box R terms. So 3 curvatures, but with a 1 over box.
You need some dimension there.
No, it's dimensionless.
R 1 over box R?
R squared 1 over box R. 1 over box can be applied in various ways. It could be 1 over box 1 minus
that's
box
fine.
2.
Yes, but this would be, that's what I was, okay, I mentioned this, if you noticed. We dropped this term because the Wilson coefficient is not known, as far as I know, for the unique EFT.
No, those come with fixed known numbers, which are categorized in a very long paper by Barvinsky, Vilkovisky, and collaborators.
Okay, but that would be.
I should maybe turn the floor over to Andrei if he'd like to say anything, but that's really the third order in the curvature corrections.
But that's a non-local term, right? So it's
a non-local term.
Yeah.
But it dominates way over the local term.
I mentioned that we were dropping those at this stage, and
but you can't consider the local dimension 6 term.
The value of doing this is that it illustrates what's happening when you have a real correction to the metric, and that's why we know that this part is not complete, because we haven't taken non-local parts into account.
Yeah, but you haven't considered those guys.
That's what I'm saying. We agree.
Yeah, so so you shouldn't go to the local 3 curvature term.
I mean, as you know, there's the non-local Wilson coefficients are probably very tiny, and then if you have an effect that is relevant is probably from the local one, which can be much larger because they're free parameters at this point.
Yeah. No.
Okay. Well,
I'm trying to.
maybe later you can discuss with more details, but okay. Luca, you had a question?
No, I think Herald is saying something. Please unmute your
Sorry,
microphone.
Who? Me?
No. Yeah.
Can you hear me?
Yes, now yes.
Yeah.
Okay,
A
sorry.
short comment. I just had a short comment in that last two speakers that I would strongly advocate the use of the Penrose diagram for the eternal black hole. Because I saw Zumba to make a couple of comments about Bob and Alice disappearing behind the horizon and so on. And the question was, where does the information go? But you can avoid all that by taking the eternal Penrose diagram and consider the Cauchy surface to rotate, to pivot around the origin as time goes on. That would be the only natural thing for the Cauchy surface to do in that diagram. And then Bob and Alice will never enter into the forbidden regions, and they would never even close to the singularity. So you can avoid a lot of problems that way. Sorry? Can you repeat that?
No, sorry, I think it was a problem with the mute. It was muted. Please go on.
You can continue. I think it was some other noise.
Yeah.
No, please, Gerard, you can continue. There was some noise in the background.
Yes. So I would strongly advocate the use of the eternal Penrose diagram, the diagram for the Penrose diagram for the eternal black hole. And then use the fact that there are two timescales. There's a very short timescale at which you travel through the whole entire Penrose diagram. That's a very short timescale compared to the timescale where the background changes, like the change of the mass of the black hole, or the effects of ingoing matter causing the implosion that made the black hole, and the effect of Hawking particles, the back reaction of that. All those are very small. So if you take two timescales, you can make very accurate approximations where things linearize. So people talk about nonlinear effects, but the effects that you then need to use to get the energy eigenstates are totally linear. And to get the energy eigenstates, of course, you need the eternal background. Otherwise, you can't get an eigenstate of anything as time goes on. So, and this way you get a very complete picture of, if in fact also the microstates, because there are then more microstates than you really need when you count the entropy. So and in that way you only use mostly conventional gravity, conventional standard model physics. You don't need much else unless you come very, very close to the origin of the diagram at a few Planck scale distance. Then you get important effects that are outside of the picture, but they are very small. They're very small corrections. And of course, it's interesting to consider very small corrections, but not if you haven't yet understood the grand picture. And that's my complaint against many researchers. People have not yet understood the grand picture. If you look at the entire Penrose diagram, you find that there are two asymptotic regions rather than one, which can only mean that they refer to different parts of the same black hole. I've had discussions with many people, and they don't believe me, but all I would like to say is that it works extremely well, and you get a very good picture about the microstates. But of course, you're not solving all problems. There are still things that you want to sort out.
Yeah, no, it's very nice that you raised this point, and I'm glad that you. So let me understand your picture a little bit better. So what would happen? So you would say that Alice and Bob would never reach the singularity, or you want to somehow cap the singularity and open up white hole
That's
region?
a very important question. That's a very important point. But Alice and Bob, if you throw anything inside the black hole, of course it goes to the forbidden region. However, it also leaves a gravitational footprint behind. That's a Shapiro shift. So Alice and Bob do two things. They move to the eternal region, say beyond the horizon. That's time equals plus infinity, infinity plus something else. That's one thing they do, but also they leave gravitational imprints behind. And those gravitational imprints contain all the information in Alice and Bob, and that goes out as quickly as Alice and Bob went in. So the information is conserved in that way. Which is very important effect. So once you say that, you say, okay, the Alice and Bob which went into the black hole, if you take those into account, you're overcounting states. So you have to count every state only one. So the information that Alice and Bob brought in is pulled out gravitationally at the same moment. So you don't need the other information that Bob and Alice introduce in beyond the horizon. You can just forget that. So that would be the rule, and that rule makes everything unitary, no information loss, and in fact calculable states.
So if I understand, so essentially, so you would say that essentially you are bringing the picture of holography. So somehow before even entering into this forbidden zone,
it's not really holography.
You have got all the information on some surface.
I don't know whether you can see now
you can see your screen.
This is the diagram I'm talking about. Can you see it?
Yeah.
And it contains the Penrose diagram for the eternal black hole with two asymptotic regions, plus a Cauchy surface, which moves up here and down here. So Bob and Alice will always sit on that Cauchy surface. And as far as the outside observer goes, the outside observer, of course, never sees Bob and Alice actually go through the horizon. They just see them approaching the horizon exponentially fast. What happens then is that gravitational fields become very significant, and the gravitational waves that they emit then come out and represent all the information they contain. So we don't need the extra information that they deliver to these beyond horizon regions. This turns the black hole into something completely empty, not only empty of information, but also empty of space-time itself. There is no space-time inside the black hole horizon. There's these two regions, 1 and 2, which is both outside the horizon. And what I did next was to say that region 1 and region 2 are actually related to the same black hole. They represent two hemispheres. If you postulate that, it's a major departure from standard wisdom, but if you accept that, everything falls into place, and you understand the microstates just referring to one half of the black hole, the other half of the black hole.
I see.
All I can say is I advocate this picture because it
amount
looks
of non-locality embedded in it. So you would say that so there is some amount of non-locality embedded in the system then.
Well, the non-locality is in the identification, and the identification comes about because you are removing the ingoing matter. You are removing the outgoing matter from the picture. And so the space-time beyond this point now is now something totally different. And that something totally different now joins onto the other hemisphere of the black hole, which is a postulate. But once you make that postulate, everything falls into place. Even the formation of the black hole can be understood. So, so from that moment on, you get complete eigenstates, you get conservation of information. And of course, you can do higher order corrections, and I welcome everybody to try to do that. But those are minor effects, and you first want to have the major effects in order, and that's what I would be advocating.
Can I ask how can you use this for a black hole that it's formed by gravitational collapse, right? Which is not an eternal black hole, because
gravitational collapse is not visible in this picture. All right, so I don't see gravitational collapse taking place here, but
this is exactly the question.
So the entire past horizon is an infinite past and therefore not relevant for short time scales. So for short time scales, you don't have to worry about that. At a long time scale, yes, you do. But that's another question. At a long time scale, the black hole slowly changes appearance. It becomes larger or smaller if things go in and things go out. And you can take that into account. But that time scale is so slow that it has no effect on the very short time scales where much more important things are happening. So by gluing the two time scales together, you get the complete picture without any internal contradiction as far as I can see.
Okay, I really would like to continue this discussion, but probably it's better if we go on and we move it again to the second discussion section, which will be very, very long. So Bob Oldham, I think he had a question from quite some time. Now, go ahead.
Renault's talk mentioned an old paper of mine, and it reminded me of a result in there, which is if you have a fundamental theory with a general set of terms that include 6 or more derivatives, then there is no Schwarzschild solution. So I'm just wondering whether that's been considered as a constraint on construction of theories with many derivatives.
Okay. Can you hear me?
Yes.
Yes. Well, what we did was to look for the solution generated by a point-like source, and we did it analytically. It was not numerically. So we started from the source, and then we obtained the field. As far as I remember, in your case, you did a numerical search for solutions using an ansatz of the series, Frobenius series representation, right?
Yes, it was just an analysis around the origin for the full nonlinear case.
Mm-hmm. But in that case, this is always a question that I wanted to ask you. Did you consider which kind of terms in the action? Was it the most general action with that number of terms, or it was only like R cube, or did you also include the kinetic terms?
The what terms? I did try to include the most general set of curvature invariants. Yes.
Mm-hmm. And in that case, you couldn't obtain Schwarzschild, right?
Well, I couldn't obtain any singular solution at the origin. Mm-hmm. I seem to conclude that the only solutions available were non-singular solutions at the origin.
Yes. In this sense, I think that our result is like a linearized version, but very weak because we consider only the delta source. And of course, if you put other sources, situation can change.
And so people who do non-local theories, are they taking a particular class of theories that ensure that there are these, or in particular, black hole solutions?
Yes. Sorry, Bob, could you, I didn't hear it.
I assume whenever you write down a theory, you always check that a black hole is actually a solution to the theory, right?
Yeah.
So in that sense, you're not in this general class of theories that I'm talking about.
No.
Yeah.
So what we found that when you put any known black hole solution, even most singular solutions, they don't solve the equations of motion, classical equations of motion. Is the wild term which prohibits it.
You said even more singular solutions?
No, so far we have not found any singular solution.
Any what kind of solutions?
Even if you take, say, a very singular solution, let's say as an ansatz, let's 1 over r to the power alpha, it's a very singular, and you put it in order by order in, order by order, say, order in derivative. So one box square, box cube, if you run it through, you see that you don't satisfy the equations of motion order by order in box, unless until you require huge fine tuning to cancel them. And that doesn't happen usually.
I would add a little bit to this. Actually, we even was coming to an idea that maybe this is actually the way to resolve the singularity, because you see these high derivatives ameliorating UV behavior, they must ameliorate somehow something the origin of the black hole. And what we found that most likely the conformally flat story is restoring, conformally flat background, conformal flatness, let's say, is restored in the origin of would be the black hole. So you would not name it a black hole anymore. And we have an idea that maybe this theory intrinsically forbids something singular.
But for example, I find for example, when I say non-singular solution, then this metric function that I call A of R has to equal 1. So if you do want a solution that has a horizon, then it will have to have another kind of a horizon to get back to this condition that A of 0 has to equal 1.
Yes, it should have at least 2 horizons. It should, but we are lack of exact solutions. I totally agree with you that one horizon will be forbidden by Penrose-Hawkins theorem just as such. So yes, you need second horizon.
So it's possible there are no solutions with any horizons in these theories.
No, what I would say that I would expect solutions which have inner and outer horizons, but I do not expect solutions which are singular.
Which are, sorry, what?
I do not expect singular solutions. So yes, let them have 2 horizons. Let's say even number of horizons, okay?
Yes.
So that you don't, you should not change topology at the end of the day.
Right. Have you searched for such solutions numerically?
Yes, we tried, but the task is extremely complex. You know?
Yes, I agree. Yes.
So
I have an impression that the 0-0 class of solutions, which you have discussed in your paper on fate of singularities in higher derivative gravity, those class of solutions may only remain in non-local gravity. Other 2 for sure will not be there. 1 - 1 and 2 2. But okay, well, to be exact, solving equations of motion is pretty much difficult, as Alexis said. But I think I believe that 0-0 class, some 0-0 class of solution should exist with 2 horizons.
Maybe one last comment that even though it's difficult, but there are ways one can solve it. I think you require some certain geometric ansatz. Like here we were solving with the help of ansatz, but maybe if you go to almost universal class of space-times, then there may be some solutions you can find. Also in lower dimension, even 1 + 1D, you can try to find some exact solutions. So so the problem is it gets harder and harder in higher and higher dimensions, but maybe one can learn some intuition from 1 + 1D where situation gets much improved. But so it's hard, but not completely. So one should try, definitely try.
Sorry,
ask one thing. If you realize that the singularity is beyond the infinite future or beyond the infinite past, but not at the center of the black hole, as people usually say. In other words, there is no problem with that singularity, as far as I can see. It's like a singularity in the complex plane, right? If you look at the planets moving in orbits around the sun, you ask what happens at complex time. Well, they go through branch cuts and things like this, but that's of course totally unphysical. And in the same sense, I consider the singularity of the black hole as unphysical. I think cosmic censorship works very, very well for the Schwarzschild black hole and for most others as well. So I don't know in what case it's only in very artificial cases it does not hold. But so I don't see why people have difficulty with the singularity.
And how about the cosmological singularity, Gerhard?
That's something else. So the initial singularity of the universe, that's how the universe got started. And that's indeed a question a little bit beyond me. But yes, there's a problem there. But that's not the singularity of the black hole, not of the ordinary Schwarzschild black hole. And those singularities are outside the physical domain. So I see no reason to worry about them. or to complain that you want another solution which has no similarity there.
I think Gia had a question for a while,
but you do have several that reach it in finite time, right? The singularity.
Well, for the internal observer, yes. So the Bob and Alice who went into the black hole, they think that they reached the singularity at a finite time. But I'm saying, well, we should exclude those Bobs and Alices, because that's what happens at time equals beyond infinity for the outside observer. So for the outside observer, this is a no problem, because the only problem is, what do Alice and Bob do now, and how do we conserve their information? And my answer to that is, as I just said, that the information is carried away by the gravitational field. So yes, it comes out in the open, it can be measured. But what Alice and Bob do when they do reality is totally unphysical. We don't care about that.
But this is also ignoring the evaporation, right? Because otherwise you will reach it.
So you will be overcounting states. Right? Every quantum state can only be counted once, as we know. Otherwise, something doesn't work in quantum mechanics. So don't count Alice and Bob twice. And the second counting that you should not do is the counting that they are beyond infinity for the outside observer in time. So they're not in the physical domain of science, so to speak.
Gia, I see that you have the hand raised for quite some time. I'm sorry, but so you can.
Initially, I had something about conversation between Gerald and Anupam, but then meanwhile many interesting comments were made. So it's yeah, there are many interesting questions. But anyway, let me come back to this thing, because of course, I mean, the nice thing about this conference is that we come from different approaches, and it's very important to find the touching point. And so in this conversation that Gerald and Anupam had at the beginning, so Gerald, you are, by some reason you are insisting on having an eternal black hole, which I don't understand. What is the gain, or what is the meaning of that, or what you gain with that? Because let me say why. Because let me say why. Because you said that for an eternal black hole, corrections are small, but actually that's not true, because we have to compare corrections over the black hole lifetime. That's what matters for the information recovery, not the correction in 1 second. And therefore the corrections, they go as 1 over black hole lifetime for arbitrary black hole. And therefore, I mean, taking black hole to be eternal, you are not gaining anything.
I think this touches upon a topic that we just called yesterday, I think, about the estimators, that you thought the estimator was the most important thing. I'm saying, no, I want to know what happens locally. So the same thing here, in the case of the black hole, I want to understand how the black hole reacts now, a second from now, and a second ago.
No, that's very interesting. But then you are not. But then you are not addressing the information problem, because information issue is that the information that goes in should come out. Information, it doesn't have to come out within 1 second.
Would you agree that if I say in 1 second the information is being conserved, no matter what the black hole does? So if it is conserved over 1 second, it will be conserved also at the infinite amount of times.
No, because for example, I can have a box. In which we can put a book, and then I can keep this box completely shut for 1 hour and then open it up. So what?
During the 1 hour that the box is shut, the book might be decaying.
We're not getting any information out of it.
The book inside, and so things are happening, and you can open the box. But you can do the same thing with the black hole picture that I was advocating. You can do the same thing for a finite time. Before asking the question what happens at infinite time, you have to answer the question what happens at finite time, and then glue those events together, and you will find out what happens at infinite time. There's no secret.
Of course, but the corrections at so if you are taking an eternal black hole, because I'm giving you an answer that I see from S matrix. From S matrix, I see that the time scale for coming out of information is given by approximately by black hole lifetime. Now, therefore, if you are taking black hole to be infinite, on any finite time scale, you will not get any significant portion of information out of it.
But would you say such a thing for the hydrogen atom? If you want to study the state of the hydrogen atom, the things it does, do you want to know how it was formed, how it will decay a billion years from now? That's not relevant for its present behavior. So what we want is
hydrogen
a locality of information, so to speak, also in time. So information.
But the rate, what I'm trying to tell you,
disappear for a million years and then come back.
But what I'm trying to tell you is that we see that explicitly from the microscopic picture. We see that the rate by which information is coming out depends on how big is the black hole. We cannot change the fact.
That's true.
So that's a fact. So therefore, and the rate is always given by inverse lifetime. So therefore, it's
the same true for the
impossible
hydrogen atom.
Hydrogen atom is a very different system. It's not a saturated system. Hydrogen atom is.
I mean, for me, it's exactly the same thing.
Well, that's the mistake you are making if you are saying that it's the same. Because I'm telling you it's not the same because that's what I see. No, but look, I mean, I'm just saying. So what I'm saying is the following. From microscopic thing that may be completely wrong. I'm not saying that necessarily my microscopic picture is right, necessarily S matrix is correct or something, but it's an A picture from which I see something very concrete. What I'm saying is that I see from that picture that the rate is suppressed by inverse lifetime. So therefore,
sorry, what is suppressed? What is suppressed?
By inverse lifetime. So the fraction of the fraction by which information comes out cannot be faster than 1 over half lifetime of a black hole, at least until half decay time.
I think that is based on one thing that you neglected, which was the gravitational information of things going in that moves, displaces things coming out, and that happens very fast.
No, Gerald, I cannot be neglecting anything because I'm doing computation. I'm doing S matrix computation. Yeah, I'm doing S matrix computation. I'm reporting what it does. Okay, so let's assume that I didn't make a mistake and the two groups didn't make any mistake because they got the same results. So all I'm saying is that computation tells me that the rate cannot exceed 1 divided by half decay time, at least up until half decay time. That's all I'm saying.
What I'm saying is I can just do the calculation of the gravitational effects of ingoing matter. That effect explodes exponentially in time, so very, very fast compared to the lifetime of a black hole. And
well, that's a different calculation.
That information comes out immediately. And that's
a different calculation.
The Hawking radiation contains that information and it gets out that fast.
No, you and me, we completely agree that Hawking radiation contains information. Sooner or later, the information comes out. That's not the subject of our dispute. What I was trying to tell you is that you have to be careful when you are taking an eternal black hole. The corrections, of course, over any finite lifetime are small, but what is important for is the integrated life. What happens over integrated life of a black hole? And since in my picture, the corrections go as 1 over t. Huh?
Don't you think the same thing happens for a hydrogen atom? And also there.
No, it doesn't happen because
that it emits or absorbs is also processed inside for some time and then it gets out. But,
no, but hydrogen atom is not a saturated system. This is what I was trying to say. It turns out that there are certain systems in nature for which entropy is equal to 1 over inverse coupling. For the hydrogen atom, entropy of the hydrogen atom is not equal to 1 over inverse coupling. Actually, entropy is negligible.
Take a bucket of water, which is agree that.
Yeah, it's not a saturated system. No, it's not a saturated system. The entropy is negligible compared to the inverse coupling for the bucket of water. So bucket of water is way below saturation. So it has nothing to do with the black hole. Hydrogen atom, the same thing. There are certain systems that are saturated, and I'm just reporting what I'm observing. I'm observing that in an S matrix approach, those systems for which the entropy goes as 1 over their coupling, 1 over the coupling in this instance, those behave like black holes. And for those, this property is universal. So therefore, by taking an eternal, you are not really gaining anything because taking eternal diminishes local corrections. The derivative diminishes, but the integral is the same.
Would you then not agree that you can have a Cauchy surface with all the particles on the Cauchy surface? They do things in, they do things out, but the Cauchy surface just evolves in time. And that's how we compute things everywhere in physics. So why not here?
Well, maybe I didn't do that calculation. I'm just saying I can only talk about calculation that I did.
My claim is you can do that calculation. Things
Probably.
go in. The Hawker particles, well, they don't get out very quickly from the entire horizon, and that's because they have an enormous potential well. So they come out, most of those particles drop back in, just like a bucket of water.
Maybe, yeah. I'm not contradicting
Only
necessarily.
affect their neighbors, but they never send their information all the way out. So it's the same thing here.
Alice and Bob never goes inside your trapped surface. That's the whole point he's making.
Pardon?
I understand. In your case, suppose if I had to solve dynamically, your Alice and Bob will never go inside the trapped surface.
That's right. So and what is there instead is the gravitational information that does get out very quickly. So, but then most of those particles will be orbiting the black hole at a very close distance and then fall back in again.
Gerald, so in order to compare our understandings, we should find a touching point, right? So we should find certain invariant notions that are invariants for me and for you. The only invariant I see in our approaches is that the total information has to come out. Okay, that you agree, you and I fully agree with you, and we agree with each other. That's an invariant statement. So yes. I have some now
sorry to interrupt you guys. Sorry to interrupt you, but we are starting the next section in 10 minutes.
Oh,
so I would like to give you the floor just very quickly to Strobisky, that I've seen that is the hand raised for some time.
Sure.
But maybe very quickly if possible, and then we will have some very short break and come back. And
very quickly. Yeah. So just to summarize. So since we have this one invariant notion that you and me agree on that, so now I'm saying I know how to compute this thing in an S matrix approach, and this is what I see. And what I see is that the time scale over which this has to come out is given by half decay time. Okay, so to start coming out.
True, I think.
Sorry.
You're making assumptions about how the information comes out and from where. But
no, I'm not making any assumption because I'm just doing. That's the power of S matrix. I don't have to make any assumptions. I'm just computing it. You give me S matrix rules, you give me vertices, and I just compute and report what I get. That's it. At no point I'm making any assumption.
I can very well imagine that there is no strong disagreement there, but I just want to chop the time axis into small pieces and ask what happens from second to second to second, and not immediately what happens from minus infinity to plus infinity. I mean, think of the
yes. I understand. All I was asking, what do you gain? What do you gain by infinity? That's what I don't see. What you gain by infinitely eternal black hole. This is what I don't see.
Think the archaeology of the Earth. Think of the continents on the Earth, and you want to know how did the Earth get started? Well, it got started by planetesimals that made the Earth. And how does it end? Well, it ends with some nuclear explosion because the civilization went at war. So, and now don't you want to know how it went from the beginning to the end? Lots of things happened.
This is part of your assumption that you are trying to make sense of the white hole.
Let's make this the starting point of the second discussion section.
Yeah, no, that we should discuss.
I'm very sorry.
I think we have no time.
Many talks.
I would say we have no time for more questions, Francesco, maybe.
Okay.
Maybe just the last.
I have a proposal. Okay, I would like to make a proposal, but actually for not this discussion, but the discussion to which will take place at the end of this day. And so my question I'm asking first Professor Croft, then Gia, and actually all other participants to think about their answer to the following question, which is much less academic than the discussion about eternal black holes. We actually see from our gravitational wave about observations, the emerging of the black holes with, say, typically of 10 or more solar masses, and this process that finishes in about 10 in power -4 seconds. So my question is, do you really think that as a result of this process, that total entropy in the universe increases by fantastically large factor 10 in power 80, which is actually not much less than the entropy of the whole cosmic microwave background in the whole volume inside the last scattering surface? Or you have some other opinion about the growth of entropy in this process?
May I briefly answer? I think that the question is not fundamentally different from if you have two buckets of water colliding and making it one big bucket of water, and the whole thing heats up while that collision takes place. So also lots of entropy is being produced.
But fantastically much less.
Well, okay, the numbers are totally different. I agree with
about
that.
numbers.
Numbers are very different. But
actually, Gerald and Alexei, actually, one micro comment, because actually the entropy that Alexei quoted, 10 to the 80, is a tiny fraction, 10 to 80, right?
Yes, yes.
Yeah, that's a tiny fraction as compared to the Gibbons-Hawking entropy of our universe, which is 10 to the 100 or 120 or 132. And that's the key.
Once more, I don't think it's correct. When I actually, as I said, I compared
Gibbons-Hawking entropy is the Hubble times and Planck square. I mean, that's what Gibbons-Hawking entropy is. And Planck divided by Hubble squared.
Once more, I compared with the actual entropy we see in the cosmic microwave background, that is 10 in power 90. But still,
yeah, but that's also a tiny fraction. Gibbons-Hawking entropy is the dominant one. Gibbons-Hawking entropy is the dominant entropy of our universe. If we dismiss it, then we are missing a huge portion. We are missing an elephant in the room.
But Alexei, do you see a problem there? Is there a contradiction you talk about, or is it just
it's not.
Entropy increases very fast?
A contradiction. It's fantastically fast. You growth of entropy as compared to all what we have, indeed, as you mentioned.
No, that I agree. Delta S. Delta S is large. Yes, that I agree with that. Yeah. So you have a point that delta S is large in the matter sector. That I agree with. But that also should be taken into account, that all of that matter entropy is tiny fraction as compared to gravitational entropy of Gibbons-Hawking.
Once more, we have only 5 minutes before the next section, so let's have a very short break, and then we will try to conclude this discussion.
No, Alexei, you have a very important point. I'm not contradicting to you. That's a very important point, a very interesting question. It's just why delta S is large in the matter sector. So sure.
In other words, from one statement is the fantastic huge amount of information is lost. But from our naive feeling, we knew nothing about this lost information. So
no, we know something, and let's start the next discussion with that. I want to answer that question actually from my perspective. Yes, thank you.
Okay. Next discussion will start with
once more.